Okay, so now that we've talked about sequences in more detail, we're going to start talking about series. And it's not a type of series that you watch on Netflix. What series means here instead is what happens if we add up all the terms in an infinite sequence. Okay, so I'm going to start with an example here. For instance, the sequence a sub n is equal to 1 over 2 to the n. So that's the sequence 1/2, 1 over 4, 1 over 8, and so on. And the question is, what do you think happens here if we attempt to add all the terms of this series together? Okay, so there's infinitely many terms here, right? So does that even mean anything in the first place? Well, let's see. I'll draw a number line here. And I'll mark a 0 here. And I'll mark a 1 here. And what I'm going to do is I'm just going to, well, start adding terms one by one. So 1/2, so starting from here. Let's add 1/2 to our sum. So let's keep a running total, right, of what we're adding up. 1/2 is, well, right in the middle of this interval. So you add the first term and you end up here. Okay. Now let's add the next term to 1/2. So it's 1 over 4. So 1 over 4 takes us, let's see, is that halfway? Yeah, this is about halfway there. And it actually takes us to 3 over 4, right? 1/2 plus 1 over 4 is 3 over 4. And now we end up here. And let's do it one more time. Let's add 1 over 8. Now from 3 over 4 to 1, this interval now is just 1 over 4, right? Its length is 1 over 4. So when we're adding 1 over 8, what that means is we're essentially moving halfway closer to 1. Right? And I mean, let's do it one more time if you want. You can probably guess now that this next running total, right? This next term in our running total here is now 15 over 16. Once you've added 1 over 16 to 7 over 8. Okay, so what do you think happens here when we keep adding to infinity? You notice that at each step, right, when we're adding each term, you're getting halfway there to 1 at each step, right? But also notice that because of that, we don't actually get all the way to 1, even if we're adding all these terms up together. In fact, I can represent these running totals as, well, I'm going to call them partial sums. It's a more formal term for it. But again, it's essentially, let's start adding and keep track of where we're at after each term. So I'm going to call S sub 1 the sum of the first term, and that's it. Right? So it was this 1/2 here that we started with when we added the first term. S sub 2 was our running total after 2 terms, and this was 3 over 4. S sub 3 is what we get after 3 terms, and that's 7 over 8, and so on. And so from here, using that fact that I mentioned, right, that every time we add something, we're essentially moving or closing a distance that covers half of the remaining length to 1. In fact, I can actually write this in terms of how much distance there is left to go to 1, right? So 1/2 is 1 minus 1/2. There's 1/2 left. 3 over 4 is 1 minus 1 over 4. There's a quarter left at that point. 7 over 8 is 1 minus 1 over 8. 15 over 16 is 1 minus 1 over 16. And what we're going to guess here is S sub n Right? What happens if we add the first n terms, right? Can we actually get a general expression for that sum? Well, we're going to guess that it's actually equal to 1 minus 1 over 2 to the n. Right? And again, that makes sense, and that agrees with intuitively what we've seen so far. But now take a look at this expression. 1 minus 1 over 2 to the n. What happens as n goes to infinity? Okay, so we can try taking a limit here. In fact, 1 minus 1 over 2 to the n, all these terms here essentially form a sequence of s's, right? S1, S2, S3, S4, Sn, general term, 1 minus 1 over 2 to the n. So it's a sequence, and we can check whether that sequence has a limit. And in fact, it does. 1 over 2 to the n simply goes to 0, so this is 1 minus 0, or 1. And in this case, we would be justified in saying that maybe we can write something like this: 1/2 plus 1 over 4 plus 1 over 8 plus dot dot dot, to represent we're adding all these 1 over 2 to the n terms forever is actually equal to 1. Does that make sense for you? Are you happy with that? Think about it this way. Remember from before that we were talking about what happens when you take an integral of an infinite area. And what did we do there? We said that if this limit exists, limit as t goes to infinity of the definite integral from 1 to t, then we'll call this the value of your definite integral, right? Your improper integral from 1 to infinity. Right? So you cut it off at t, but you let t go to infinity. Well, aren't we doing something similar here? Let's cut it off at n, right? And then let n go to infinity. And here we're seeing that we're getting 1. And that's very interesting, right? And in fact, let's formalize it a bit more in this slide. For any sequence a sub n, we can actually form what we'll call an infinite series using this sigma notation that you've seen before. Summation of a sub n from n equals 1 to infinity. And yes, the upper index here is infinity. The upper bound is infinity. So it's just a1 plus a2 plus a3, etc. This is what is called an infinite series. While this term here, 1 minus 1 over 2 to the n, that general term you get when you cut it off at a sub n, right? It's dot dot dot, but then a sub n is your last term. We'll call that our nth partial sum. And in fact, we're going to define your sequence, your series, to be convergent if and only if the limit of the SNs exists as a finite number. And so in this case, we're just going to say a sub n, sum from n equals 1 to infinity, is equal to s, right? Whatever that limit is. Otherwise, if this limit does not exist, then we'll say that this infinite series is divergent. Right? And just as a reminder here that you should be careful, because convergent and divergent here, as referring to series, means something different than convergent and divergent for sequences. It's very similar, right? But they define different things in relation to these objects. So let's do another example here. Let's look at the sum of the sequence with terms a sub n is equal to 1 over n times n plus 1. Right, so that's a rational function, n over n plus 1. What do you get there? Well, this infinite series is going to look something like this. So when you plug in 1 over 1 times 1 plus 1, that's 2. N equals 2 gives you 1 over 2 times 3. N equals 3, 1 over 3 times 4, and so on. Right? So that's what your infinite sum looks like. And now, let's look at what your partial sums are. Right, from the previous slide, we said that if the limit of the sequence of partial sums is convergent, exists, right? If the sequence of partial sums is convergent, then the series is convergent. So let's look. What's S sub 1? So S sub 1 is equal to just A sub 1. It's just the first term, so it's 1/2. S sub 2 is A1 plus A2. It's 1/2 plus, well, that's 1 over 6 now, which gives 2/3. Right, that's 3 over 6 plus 1 over 6. S sub 3 is A1 plus A2 plus A3. And that's 1/2 plus 1 over 6 plus 1 over 12. We already know that 1/2 plus 1 over 6 is 2/3, which is 8 over 12, right? So this is 9 over 12, or 3 over 4. And you can do one more. In fact, we can actually write it in this way. S4 is S3 plus the fourth term, right? Mimicking what I just did for here. That was S2 plus A3, right? So S3, the sum up to the third term, plus the fourth term, gives you the sum up to the fourth term, right? That makes sense. So this is now equal to 3 over 4 plus 1 over 20, and that's 16 over 20, or 4 over 5. And this looks suspicious. See the numbers that we're getting. 1 over 2, 2 over 3, 3 over 4, 4 over 5. And I'm going to make a guess here. Hey, maybe S sub n, my nth partial sum, is actually equal to n over n plus 1. Well, is that true? It makes sense from the first 4 terms here of your partial sum sequence. Can we actually prove it so? Well, I'll give you a second here to think if you want. Try to figure out how we can get S sub n here. This is in fact the correct S sub n. Okay, so if you want to work this out, pause the video right now and try to figure it out. Okay, so did you get it? If not, I'll give you a hint. In fact, I'll just do it. This a sub n term, which is 1 over n plus 1, it should remind you of something that you've seen before. Right? It should remind you of partial fractions. Right? It's a rational function. The denominator has been factored into 2 linear terms, so we can apply your partial fraction decomposition. And it's a pretty simple decomposition. It's just 1 over n minus 1 over n plus 1. And so, when you try to write out S sub n, well, this is a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. What's a sub 1? Well, using this decomposition, now I can write this as 1 over 1 minus 1 over 2. A sub 2 is 1 over 2 minus 1 over 3. A sub 3 is 1 over 3 minus 1 over 4, and all the way to 1 over n minus 1 over n plus 1. Okay, and so what happens next? Well, minus 1/2 will cancel with this plus 1/2. Minus 1/3 will cancel with this plus 1/3. So will this 1/4 with the next term, and so on. The pattern just repeats until this 1/n cancels with minus 1/n in the previous term. So S sub n is just going to be equal to 1 minus 1/n plus 1. In fact, this is equal to n/n plus 1. Aha! We can remove the question marks here now and just keep the smiley face, because this is now proven to be true. Right? And this is what is called a telescoping sum because of its behavior. Right? Kind of like a telescope that you can expand or contract. I don't know, do they still make those like that these days? But this is called a telescoping sum, when the terms cancel from one to the next. Therefore, the limit, as n goes to infinity, of S sub n, this sequence of partial sums approaches 1. Right? n/n plus 1 approaches 1. So the series is convergent to the number 1. And that's it.